delivering mission-ready solutions, AI-powered, software-defined, and commercial-first. Combining deep mission experience with commercial partnerships, Booz Allen is defining a new defense industrial base. A network that crosses traditional boundaries to scale non-traditional technologies and brings our best tech to the hands of the warfighter faster, effectively delivering technology for today and tomorrow. Booz Allen, accelerating outcomes for today's warfighters.
Hello and welcome to the Emerging Tech Horizons podcast. I'm Arun Seraphin, Executive Director of NDIA's Emerging Technologies Institute. On today's episode, we're going to talk about an emerging technology, or arguably an emerged technology, that can reshape the way we think about aircraft, aerodynamics, and even flight itself. These are adaptive morphing control surfaces. And we're going to talk about what that concept means for the future of aerospace and defense. In theory, could potentially save millions of dollars in fuel costs or enhance the performance of our high-end military fighter aircraft or civilian aircraft. To help us guide us through that landscape and tell us what the future holds in this technology area, I'm joined by Dr. Sridhar Kota and Hal Chrisman from FlexSys, an NDIA member company working on these novel structures. Sridhar is the founder and CEO of FlexSys, which he founded in 2001. Hal is the president of FlexSys, and he's a seasoned aviation, aerospace, and defense professional with decades of experience in the industry. Sridhar and Hal, welcome to today's podcast.
Thank you, Arun.
Thanks, Arun. Thanks for the opportunity.
So, Hal and Sridhar, I didn't give you any justice on your bios or background, so here's your chance. Hal, let's start with you. Tell us about your background and how you got to FlexSys.
Sure. Well, decades is the right description. I've been in the aerospace and defense industry for 39 years, so almost 4 decades. Began my career as a project engineer at Williams International on the cruise missile engine program. While I was at Williams, I got my MBA at the University of Michigan. Go Blue. And since then, I've split my time pretty evenly between executive roles in industry and management consulting. I've been blessed with a pretty diverse background. I've helped develop strategies for some of the biggest players in the industry, particularly within the sustainment and MRO markets. And I was a member of Oracle's Aerospace and Defense Solutions Center. I ran marketing business development for a startup e-marketplace back in the dot-com boom, which didn't work all the well for me. Ran corporate development for a military aircraft MRO. Went back to consulting with AeroStrategy. That's a company now called Aerodynamic Advisory, one of the better known focused aerospace advisory firms. Joined a private equity firm, ran one of their businesses, learned a lot of hard lessons, and then joined FlexSys a little over a year and a half ago. Basically brought on board to commercialize and scale the business.
That's great. Sridhar?
Well, I don't have much of a background in aerospace but when I started, I didn't have any background. I was a professor at University of Michigan in mechanical engineering. I was actually working on micro electromechanical systems in the 90s. And those devices needed was actually ability to generate mechanical motions without any joints. And also they need to run, they need like several hundred millions of life cycles. So I was thinking about how to do that and come up with an idea of making things more flexible, and the fact that they needed more, millions of life cycles. That also it has to be load bearing. So I developed this concept for developing these structures that are strong and flexible simultaneously. So one thing led to another. I came up with an idea of how you could use that approach to morphing aircraft control surfaces. I reached out to AFRL one day and said, I have an idea. And when I talked to them, they really liked the idea. That's when I heard about F-111 aircraft that they flew back in the 80s that had like 200 parts and 24 motors. And then my design had 1 part and 1 motor. And they encouraged me to continue the work. And later on, I got an SBIR and started building it. Worked beautifully. And then in early 2000s, I got phase 2 SBIR. That's when I founded FlexSys. And I must say that I have very little background in business, so this was more of a passion project for me all these years, and testing and the technology at various scales. We can come to that later on, but I must note that now that we've done all that, now the business development side, I'm very fortunate to have been able to attract Hal to lead that effort and take this to the next level.
Yeah, and I want to say, Sridhar, in addition to your technical background and your business background, I know you for your policy background. We actually had the chance to work together at the White House at the Office of Science and Technology Policy. And I will tell people that you are one of the forefathers, the creators of things we take for granted today. The National Network of Manufacturing Institutes was something that you worked very hard on over a decade ago during the Obama administration. And that idea that we need to do more in advanced manufacturing, create these places that can improve the manufacturability of advanced technologies, is something that you led, you drove, and it worked, and those still exist. And so I will always be grateful for my time that I got to work with you, and for you back then.
Well, one sec, I just got to say, Arun, thank you. But most importantly, I think your support meant so much more to me during those years, and continuing on with M4Sight and what have you. So thank you, and you made a lot of that possible.
So Hal, FlexSys works on a variety of aerospace engineering activities. Tell us more broadly what the company is, where you're located, how big you are, and all the various things you guys are up to.
Sure. So FlexSys is an aerospace products and technology company, kind of with two overlapping lines of business. The first is based on the morphing technology that Sridhar described a few minutes ago. It's really the design and production of compliant, seamless, gapless, shape-changing control surfaces. That's our core technology, and it's, as Sridhar said, the genesis of the company. The second line of business is really the support of legacy military aircraft. And that's really, development of sustainment support, repair development, performance improvement modifications, where we kind of cover the full spectrum of design, development, testing, certification, and production of performance improvements for the aircraft, whatever that might look like. As I mentioned, the first line of business is seamless shape-changing control surfaces, and we're the world's first and only company that has flown seamless shape-changing control surface and demonstrated the fuel savings, the reduction in aircraft noise, and many other benefits. For example, if you replace a traditional control surface with a morphing control surface, you reduce the weight, you reduce the cost, you improve the aerodynamic performance, you reduce the complexity and assembly time. I have yet to come up with a real drawback to incorporating this, which is one of the things I'm trying to convince a number of OEMs of that fact right now. So, you can do all that while improving the aerodynamic performance. And we're working with the U.S. Air Force right now to incorporate that technology on a legacy transport aircraft. And then, although the legacy is really rooted in shape morphing, our second line of business, where we're designing and developing modifications and performance improvements and repairs, we're developing our deep expertise, or we're leveraging our deep expertise, I should say, in engineering design, development, testing, and manufacturing know-how to offer innovative solutions for aircraft sustainment support. We're currently providing improvement modifications and repair development on military transport aircraft for a couple of different system program offices. And, those kind of cover the full range of starting at the beginning with an idea and taking it all the way through to production. And, I think that just an example that I think that makes it more real life is, we were walking around one of our military customers' hangars at their depot a few years ago and, asked the chief structures engineer what was eating their lunch. And, which is interesting. This is a good lesson in being in your, with your customer and having that kind of relationship where you could ask him that question, because he said, hey, look at this fan duct over here. We're having problems with debonding of the perforated aluminum liner from the core underneath, and the repair that they were already doing was leaving high-lock rivet heads sticking into the flow path of the engine, a quarter of an inch. And when you started doing that over and over again, eventually it began to affect the fuel consumption on the engine and the EGT and everything else, performance of the engine in general. And so we said, we can fix that. And we went away, developed the design, fabricated a prototype repair component, did the repair with them, and then supported the flight testing. And now we're under contract to, actually as of yesterday, under contract to deliver the components for that repair to the customer. So that's the kind of thing that we're doing right now on that side of things. And we're really chasing a whole bunch of people on the morphing structure side of things.
And how big is the firm? Where are you guys located?
We're in Ann Arbor, Michigan, and which is, as Sridhar mentioned, he was the professor at the University of Michigan. And we're, effectively we're about 25 people right now. We're a little smaller than that full-time employees, but we have, a number of subcontractors and DERs and people that we use on a regular basis, kind of consistently, because as dealing with the government and as a small business, there's ebbs and flows and things, and so we need to be flexible, no pun intended, and be able to adapt to that.
So Sridhar, I want to focus down on the work on the morphing control surfaces, and you touched on it in the opening. But can you sort of help us understand the basics of what you're trying to do with the control surfaces and what it might mean for aircraft?
So, as you may know, the morphing control surfaces has been an elusive goal for decades. And the approach I took to do something else, the micro electromechanical systems where you needed one-piece design that can flex and do all the things, it applies here. And this is a very different engineering paradigm in that if you look around, everything around you that is strong is also very rigid and stiff. And that's the way we've always done engineering, structures, or when you want some motion, you have complicated mechanical systems, mechanisms with all the links, joints, gears, and what have you to get the motion you need. Now, whereas designs in nature are definitely strong, whether it's a branch of a tree or an elephant trunk or what have you, they're strong, but they're flexible. So the idea of designing simultaneously to be strong and flexible is something that I developed for a different reason, applied to morphing, worked beautifully. And that's why we were able to, because a lot of people have worked on this. Number one, there are a lot of work done, like the F-111 aircraft. That's got so many parts. It works, but it's very cumbersome, heavy, it doesn't really fly, so to speak. So, but there are other programs that others have done, are still doing, using piezoelectrics and shape memory alloys, and we've done some of that in the past for a different reason. But the thing is that you have to be lightweight, of course, and it has to work through a certain number of life cycles, 100,000 or 500,000 or millions in the case of a rotor blade. So you need to get the fatigue life. You got to get the flutter performance. You have to easy to maintain and safe and reliable. You need to check all these boxes to make it practical. It turned out this approach of designing to be strong and flexible, it worked out beautifully. And so that's what we started out and demonstrated in phase one as BIR, built a little prototype with a leading edge morphing 10 degrees and all that. Then after that, again, AFRL, I should give them a lot of credit for seeing the value in what I originally proposed and encouraging it. And once they saw that in the phase two and then way beyond that, they continued to fund us one model after the other. We built so many prototypes and of different sizes for structural testing. We did all kinds of structural testing and the wind tunnel testing. And actually, one of the things, just to long story short, we actually designed and built a wing about 6 foot long and with fully instrumented and suspended vertically underneath the White Knight aircraft that carried the Spaceship One. Worked with wonderful people at Scale Composites, and the flight results we got from the flight data. That was the first time we've seen the benefit of actually morphing, because the actual benefits of morphing are very well understood in the literature for decades. People have known that. You get a high improvement in LO or D and all that. That was the first time the flight test results showed essentially can change the lift from 0.1 to 1.3, whatever we did, and then there's no drag penalty. Usually what's called a drag bucket, and that's disappeared. That's the first time. So finally, AFRL felt confident enough in the technology to say, okay, let's build a real aircraft with this now. So they bought a used Gulfstream G3, and we replaced the flaps, removed the trailing edge flaps. It's a 23-foot long section, and replaced it with a seamless control surface that morphed from -9 to 40 degrees. We also can do the span-wise twist, and we did. And NASA joined the effort, and NASA did a very good job in we designed, built, and shipped the product to Edwards Air Force Base. They installed it. They put like 3,200 sensors. Did a very thorough job in monitoring the activity throughout, and they flew that aircraft for 3 years at various conditions, 0.94 Mach to all different conditions. And we tested it before that. You can imagine, for NASA to put people in an aircraft in flight, they're somewhat risk averse. For them to do it, we had to check all these boxes. We did the fatigue life 5 times what they required, and we flew it at, we tested it for twice the design load. So we checked all the boxes. They flew it for 3 years flawlessly. They did additional 150 flight tests, acoustic flight tests, and they concluded, actually done by Langley, Dr. Karami, and others, just a very meticulous work. And they concluded it's 30% reduction in noise, takeoff and landing noise, which for us, it was a side benefit, because we completely sealed all that. There are no gaps whatsoever. So all along, this was like I originally said, like a passion project for me. I wanted to demonstrate this can be done. Because a lot of the other ideas that I have come across with using piezo's and shape memories, they work at a smaller scale, lab scale, but they're not practical by the time you put all the constraints. So that's why we were able to demonstrate and fly something that actually worked very well. I think that was probably the first time flew something without flaps, except since Wright brothers, I would say. They did it
Hal,
first.
that's the key of it, right? That there's
Yeah.
no flaps
Yeah.
on these wings.
Yeah.
And how then can you apply this to, in theory, all different sizes of aircraft?
In theory, yes. Well, the point is, the large, yes, we can. If you have a little model airplane about this size, it's not worthwhile doing it. What benefit are you going to, improvement in LO or D over that scale? So is not much. But in theory, yes. In fact, the larger the better for us, makes our life a little easier. And we use aerospace grade materials, aerospace grade actuators. So that way we don't have issues with the bandwidth, or how quickly you can actuate these things. Yes, we can do the leading edge, trailing edge, vertical stabilizers, horizontal, and we can do. We've done a lot of work. We did a lot of other things, including like morphing the leading edge and trailing edge of a rotor blade. There we used titanium material and designed it to last 200 million cycles. So yeah, we did. So over the years, thanks to AFRL, despite the challenges of government funding breaks that we all know about, but thanks to AFRL, we were able to develop many prototypes, test it thoroughly, matured it to TRL8. Now we just got to operationalize it.
So, Hal, what kind of government then, beyond the AFRL work, government partners are you working with? And you mentioned OEMs a couple of times. What kind of industry partners are you working with?
Well, like you said, we've done a ton of work with the Air Force, and now we're working with multiple aircraft OEMs. And that my real objective is getting them to the point where they see the benefit. I mean, I think they can see the benefits. It's really getting to the point that you get past the risk aversion of this is something new that they haven't seen before, and they're not really sure how to certify it. But we're doing a bunch of drag reduction stuff and performance improvement works with SAF-IE and a couple of transport aircraft programs. So that's on the legacy aircraft support. But we're also talking with, I won't go into names right now, but multiple military UAV OEMs. That's where we see the easiest adoption. You don't have FAA certification issues and concerns, because I think that one of the challenges that we face, and I'm kind of jumping the gun here a little bit, but is the certification and the risk on the FAA side of things. So for something that's civil, it's not understanding what this is. And, the word morphing really kind of brings to mind some kind of concepts that aren't natural. How does this stuff change shape? Whereas it's really not that big a problem. But most of the industry partners we're working with right now are UAV OEMs.
The potential here, if you do away with flaps and you get these structures that someday may resemble, almost as Sridhar was describing it, birds' wings, right? They morph and they shape, but they're incredibly strong. What's the implication here then on Pentagon missions? What do they gain by adopting these technologies?
Yeah, and there's a couple of ways to look at this. The couple of ways it can be applied. The way we're doing it right now, I mentioned that we're incorporating this technology on an aircraft, on a legacy aircraft right now, but the primary benefit and the most obvious is this improved L/D that we talked about. So drag reduction or improved lift, really, and you're doing that as primary control surfaces, and then with a high deflection on those control surfaces. So, at takeoff and landing, when you have, a deflection beyond 10 degrees, you begin to experience flow separation with a traditional flap. It's because you've got a sharp angle where the flap is attached and it's pivoting around a hinge. Whereas with the morphing technology, you have a nice smooth flow surface and you don't have that sharp angle. So the flow stays attached much longer. And so if you look at the improvement in L/D with you can look at it as against a deflection angle, or you can look at it against your lift coefficient. If you plot that, once you get past 10 degrees, it starts going vertical, and so you get out to 20, 30 degrees, and all of a sudden you're up at an improvement in L/D of 100%, literally 150%.
And what does that translate to in terms of things like
that's what I was going to say. The implications of that are, one, shorter takeoff and landing distances, because you're getting much better lift at slow speeds with high deflections. Improved climb gradient, so you can climb faster. You can have higher takeoff capacity, or you can trade off, between takeoff capacity or payload capacity and your takeoff distance. And coming in, you also have greater stall margins. So there's a whole bunch of benefits. The other way we're incorporating this technology is as a load alleviation control surface in conjunction with traditional winglets, or blended winglets. And by definition, winglets induce maneuver loads on the wing, just by the way they're designed and what happens when you fly them. And for older legacy aircraft, the issue there is that induced load may prohibit you from incorporating winglets on to an aircraft. However, adding an active load alleviation control surface, can inboard of the winglets, can help you reduce those maneuver loads, keeping the absolute loads within the design limits of the wing. So basically, you can incorporate a performance improvement that you couldn't have incorporated otherwise. Now, the obvious implication for this is drag reduction, because you can now put a winglet on, which reduces the drag, and you're looking at between 4 and 5% drag reduction on an aircraft. And what's not so obvious, though, is the operational benefit, which is, I think, kind of where you were headed with the question, because we've done this and we've gone through this analysis, and we're in the midst of finalizing a design on an aircraft that I can't talk about. But anyway, our customer has done some wargaming with this improved fuel consumption, and it translates into probably double the benefit and operational benefits. You don't have to have as many aircraft in the air. You can keep them up longer. You've got a lower number of aircraft in general. I mean, there's a whole bunch of details that go into that. But the bottom line is, if you improve the fuel consumption by 4 or 5%, it kind of rolls downhill to a whole bunch of other benefits operationally.
So you're talking about, if we think about the Indo-PACOM theater, and there's a likelihood that we will have ad hoc shorter runways. That's an interesting feature that they may benefit from by adopting it. But then given the vast distances and the huge amount of supply and logistics missions that have to be flown, any cost savings in this side is incredibly valuable. And I guess those are the two major, here's why you should do it. Right?
Well, exactly. I mean, you're looking at lower cost vehicles, now particularly in the UAV realm, and these are in the analysis. We did a project for AFRL where we designed a morphing control surface, and somebody else designed a traditional control surface with hinges, and they actually went through the analysis on the cost and weight, and it was 30% lighter, and it was 50% less expensive. And so you translate that into, multiple control surfaces and 1,000 aircraft a year, and all of a sudden you're talking some real numbers.
Yeah. Are there any constraints on the kinds of materials the aircraft have to be made from in order to incorporate these morphing structures?
No, you can do this with pretty much any traditional, aerospace material. We've done it in carbon fiber, we've done it in fiberglass, we've done it in aluminum, we've done it in titanium, and as Sridhar said, we've done it in a variety of sizes. We had a 23-foot, control surface on the Gulfstream 3 we flew with NASA and AFRL, whereas we've also done a helicopter rotor blade that was a 1-foot cord, and actually, that's when we were morphing both the leading and trailing edges. One was 1 time per rev, and one was 5 or 6 times per rev. So, that's where he was talking about the millions of cycles that you have to go through. And, so there's not, one of the things when I came a year and a half ago to FlexSys, one of the questions I said is that's got to break. When they were showing me their demo wing, is actually the AFRL, the G3 wing. Because it's odd to look at, when you see the surface just bending and repetitively bending. I mean, you think of what happens when you take a pen cap and bend it back and forth. Bottom line is that it doesn't do that because of this distributed compliance, and you're distributing the load so that you always keep the stresses in the elastic zone of the material. So we did, as Sridhar mentioned earlier, I think, we did 500,000 cycles of high load deflection for the G3. And, the lifetime expectation was 80,000 cycles. So, we didn't see any signs of degradation of the material.
Sridhar, it strikes me that this ability to morph structures could also be beneficial in another place, which is if those people who think about radar cross sections and signature. Am I on the wrong track there? Is there anything there to think about?
No, you're on the right track. Actually, it turns out that, whenever I made presentation about this, there's almost always, if not always, somebody in the audience will ask, hey, what about the radar cross section? We just didn't have work on it. We were focusing on getting this up to TRL level and so on. But yes, even if you take the most advanced stealth aircraft today, of course, you have the coatings, the materials that they put on coatings, and then also the active and cancellation but you want to avoid the gaps. It's one of the first principles of that. And you seal what you can, the doors. But even in the most advanced aircraft, stealth aircraft, you still have flaps and gaps and hinges. So you can't avoid that. And so this is, I think, it should. And Hal's been talking. And if you want to add anything to that, Hal. And
Well, no, I mean, I think that's obvious. I mean, it's logical, and that's one of the most things we're most excited about is that step because we've been focused on the benefits, the weight and performance and cost benefits, but this adds an extra dimension to that. And as Sridhar said, we've really not quantified that in the past. So that's, I think, one of our next steps is moving into that realm and figuring out how we do that and what the security requirements are associated with that.
So the technology is pretty mature. I've actually seen it on NDIA exhibit floors that you guys have it demoing it.
Yeah.
And the mission impact and cost impact is huge. So it sort of leads you to so what could possibly go wrong here? So let's talk about technology transition. You guys are in this strange world of not trying to transition whole systems, but kind of subcomponents to larger complex systems, many of which are probably already under contract because you're in the world of dealing with aircraft that are legacy and maybe undergoing maintenance and just in their operational part of their life cycle. So what are some of the challenges that you all are seeing in terms of trying to transition this technology into production and use?
Yeah. You want me to take that, Sridhar?
Yeah. No, go ahead.
Yeah, because I mean, I've been having dozens of conversations with OEMs over the past year and a half, and adopting a new technology like this can be daunting for OEMs. It's really because they're risk averse and focused on cost and schedule, and you've got proven components that can do what you're looking to do. So you're often displacing something that's tried and proven. So there's some perceived risk. On the other hand, you run into the not invented here philosophy that some OEMs have. But I think that the perception of quote morphing could create obstacles in itself because that's a word that people don't use very often when you're talking about wings. That's something that's been in the lab and people have been playing with, and people have failed lots of times in trying to do this stuff. But I think, and some people think that it's some new esoteric material, which is not. It's a design concept that can use any of those materials that we were talking about earlier, and just making sure that you distribute the loads properly. So we've been spending a lot of time presenting to OEMs, showing them our demo wing that you've seen, explaining the technology and helping them understand the design and the certification process, and showing that the certification process for morphing, and we've gone through a full cert plan, laid it out in detail to show this is what we believe you would have to do to certify this. And compared it to what you would have to do for a traditional control surface. And I think that the only real difference in terms of design analysis and testing would be I think we would have to do some fatigue testing, just like we did before we flew the Gulfstream 3, to prove that, hey, this really does what we say it's going to do, even though we've done it in the past. I'm sure that if we were certifying this on military or commercial aircraft, that they're going to want to see some real data on their design that proves that. So I think that the challenges are really it's really perception more than anything else. I think not, there's no technical obstacles. It's just getting people past the perception obstacle.
If I may add to that, part of that too is because there are so many efforts in the past, and even till today, you can see papers from universities and other places, labs, especially in Europe, working on morphing. And it's always an interesting video you see on YouTube, but it's not practical. And people are used to seeing that. So what we've showed is as practical as it can. We flew the doggone aircraft for 3 years under all these conditions, and we didn't have to do any repair. So the point is, that's there. Not to mention that I fully understand if you have a solution looking for a problem, that's hard to push on that rope. I know that very well. It's not that. It's not only, even when you need certain capability, whether it's noise reduction or radar cross section or whatever, fuel savings, lightweight, it's always that people who know morphing know it as something as some requires some esoteric materials and still at the lab stage. It's the lack of awareness to one thing about how mature this technology is. So that's part of that, for sure. But I think Hal's making, again, like I said, I'm glad he's doing what he's doing and I have him doing it. I'm actually blessed with extremely talented folks in engineering and manufacturing know-how, but also I must say that Hal's been really, talking to a lot of folks and making progress.
What about the more intractable parts of the acquisition process? I'll just say the requirements part of it. You describe an energy cost savings and potential life cycle cost savings that way. You describe performance improvements. You describe, shorter runway takeoffs, that kind of thing. Has those kinds of ideas found their way into the requirements that the Air Force or other services are looking for?
Well, I certainly think that it has. The last one you mentioned, the shorter takeoff, or maybe the first one you mentioned, the shorter takeoff and landing certainly has. I mean, that, as you said, in the Pacific area, there's going to be shorter runways, and all of the aircraft manufacturers that we're talking to now, takeoff performance and landing performance is probably the key thing that they're zeroed in on. They want the lower weight and less complexity and the lower cost as well. But the thing that they're really focused in on is the takeoff and landing distance, which I think obviously has been being driven by the requirements that they're being placed upon them.
Although we've been around for all these years, like I said, most of the time it was me. I had a full-time job at the university and others, but then we had the engineering talent to mature the technology and demonstrate it. But only now, after Hal came on board, we are actually getting the word out. So part of that is also us getting the word out too.
It is, yeah.
Prior to that, I haven't done much of that.
So, okay, closing question here then. If you ran the world question, what would you set as reasonable goals for the technology? Because my understanding is you're not the only people working on this. There are other people working on this, probably not as good, but there's other people who have thought about this. So what are reasonable goals for the Pentagon or the science, technology, engineering community to think about as goals for the technology and its use? And then, Sridhar, put on your old policy hat. What do we do to help it achieve those goals? So, Hal, you want to start with what's a reasonable set of technology
goals? This is a BHAG goal, and I think that our goal would be for morphing technology to be the industry standard for aircraft wing design. That you get rid of that. All of them going forward become morphing control surfaces. With the weight, cost, performance, complexity benefits that you get, I don't see why that can't happen. And I think, there's policy things that I think Sridhar can address much better than I can, but I think that enabling that really requires just kicking over the first domino, because I believe that, once you start that chain reaction and you get the first one, I believe that the others are going to look at it and say, why didn't we do that first? Because like I said, I look at the benefits of this, and I really don't see any major drawbacks to it, other than perceived risk. I say perceived because I don't think it's real risk.
Do I have to be a different kind of aircraft designer to understand and make full use of this technology? Do I have to take a different set of classes than the ones I took when I went to school on aircraft and aerodynamics?
I don't think so, because go ahead, Sridhar. You know more about classes than I do.
No, I'll answer the second question first and then go back to the first one. No, I mentioned about how, how we built optimization tools is very different than how you design structures or conventional mechanisms. That is true. It's not that difficult. We can teach, but the point is, if you want something done, we have now very sophisticated tools. It's not like we build something and see if it works for you. We begin with what kind of shapes you want to morph to, how many load cycles, what's the load. You need to provide us with that information into our tools for us to even begin to work. So when we have tools that can quickly do a feasibility study if it's possible. So while we can't quite get 28 degrees within this space, maybe we can do 25, we can go back and do the trade-off studies. But we have tools to do that. So for somebody who wants to do, they don't need to go take new classes to do it. We can show them how. We can tell them if it's even possible or not within a very short period of time because we have sophisticated tools. We don't want to waste our time working on something that's not going to work. We don't want to waste your time. We certainly don't want to waste our time. So we can do that. So having said that, going back to the idea when you talk about morphing, the benefits of morphing, you can go back and look at 1960s papers, such thorough analysis done later on when you had CFD afterwards. There's a lot of experts that have written about this, the benefits. On a clean sheet design, you can get up to 12%. That is an obscene amount. To get a 1% fuel efficiency today, if you could, they would have done it yesterday because the engines and the wings are optimized so thoroughly that it's hard to squeeze much out of them anymore. Now, they are optimized for certain conditions. Your aircraft rarely flies at that sweet spot. It's always at the wrong spot. It's like saying you get the best fuel efficiency if you drive at 53.8 miles an hour. How often you're driving at 53.8 miles an hour in your car? So it's the same thing. So the idea of to get the next generation of next level of efficiencies, morphing the shape to adapt to the flying conditions makes perfect sense. Not just to me. People have written about it decades ago. Now we have technology that's ready. So that's the reason. That's a compelling reason to make that industry standard. The technical point of view. So wherever it's possible, we would like to morph everything, but the point is we got to see what's practical. Is there a business case to be made? Number two, on the procurement side, that's a whole other challenge in terms of, at least, Arun, that you and I talk about the return on investment of taxpayer dollars. I'm actually pleased to report that, which I complain about always. It's the taxpayer funded the testing and feasibility testing of our technology, and actually the work we are doing. I'm pleased to say that they can get many times more return on that very quickly, which is good. But there's more to it in terms of the procurement. You would think whoever is working on important problems, whatever that important is, we won't go too much into it, they'll be able to look and what else is out there. We are not the only ones, we may be very good in this. Look at what's out there, and then number one, understanding what's possible, and then put some stretch goals, and then write the requirements. And more than anything else, this is going beyond what we're doing. Once you write the requirements, stop tweaking it around, because the cost plus fixed fee, companies can continue to bill you 10 times, 20 times more than what the original list said because you keep changing the requirements. So just pointing fingers at both sides, and it's not, in the end, we can't afford to have you in one aircraft at that stage. So I think understanding what's possible, writing the stretch goals, and then once the requirements are written, stop messing with it and hand it over and make it a firm fixed price contract. There's no reason why we shouldn't have those. This is broadly speaking on the policy side.
So Sridhar, Hal, if people are convinced and want to work with you, how can they find you? How should they try to partner with you? What kind of partners are you looking for?
Yeah, we're easy. We're looking for, well, actually on both sides of the equation. We're looking for OEM customers that are designing aircraft that want to see those benefits that we've talked about. And we're pretty easily. We, generally like to set up an introductory meeting with companies, and often virtual, but I prefer in person, to tell you the truth. And then we introduce the technology and its benefits and make sure they understand what we're really talking about. Then we usually get some basic data from them. As Sridhar said, we can can run a feasibility study using some proprietary software pretty quickly. I mean, I'm talking a matter of weeks, not months. And then, from there, we're pretty much like working with any other subcontractor. We integrate to a team and become part of that team, and do our stuff and work with the people whose hardware we're going to be interfacing with. And you asked about the question earlier about do you need to take some different classes? And it's not different classes, but it can be a different mindset, because here you can lay up, if you're doing a composite wing, you can lay up the full wing, including our control surface. You don't have to have it stop at the bulkhead and then have a control surface bolted on. So it's a little bit of a different philosophy in thinking about how you might design to manufacture. But anyway, going back to the other, I would say we're small enough and agile enough of a company that we can move quickly from, concept and discussion to actual product and delivering things. And we're a good customer. I mean, a good partner. I'm sorry. We work well with our customers, and, we're honest, straightforward, transparent, all those fun words that people like to hear, but you got to demonstrate and prove that they want to hear that.
Yeah, that's right. Strong and flexible. That's what we want, right? Okay. And FlexSys NDI members active in the divisions, active in our conferences and shows, so you can run into them at various NDI events as well. That's great. So Dr. Sridhar Kota and Hal Chrisman are with FlexSys. Thanks for joining us today, gentlemen.
Thank you, Arun.
And thanks everyone for listening to another episode of Emerging Tech Horizons. If you enjoyed this podcast, don't forget to give it a thumbs up and subscribe to our channel to stay up to date with all of our latest content. We're available wherever you listen to your podcasts, including YouTube. I want to extend our appreciation to Booz Allen Hamilton for sponsoring today's episode. We encourage everyone to please visit ETI's website to sign up for our mailing list, register for our various webinars, events, and educational offerings, including our Tech 101 educational series. A special thank you to Melanie Yu and Daniel Park for producing this episode. Thanks so much for joining us on Emerging Tech Horizons.